All right. Student T distribution. Very vital, very simple, very interesting. You guys need to understand that this is nothing difficult at all. It's very if you understand the Z distribution, sincerely, you don't have any issue right here. So all you need to do is to just pick up some new things that of course that separates the Z test from the T test, and then you are good to go. Very, very similar to the Z distribution, and just watch out and you will see how simple it is. Now, the major difference between a Z test and a T test is this. When you have a Z test, I told you guys that for you to decide to use a Z distribution, can anybody in the comment section tell me what I told you should happen before you decide to make use of a Z distribution? What did I say was the criteria for you to decide on using Z test? Can anybody give me that quickly? Thank you very much. Sample size being greater than 30. That's great. Now, I want you guys to know that there are lots of discrepancies around that. Some people will say different, but we just have to stick to that for the sake of the exam you have in front of you. So we have some people feel certain ways about this, but this is what we'll be using. The sample size being greater than 30, all right? Now, when do you use a T test? Of course, let me quickly say this. Student T distribution and T test are the same thing. So, a student T distribution is just a longer way of saying T test. Now, we use a T test when the sample size is less than 30 and the population variance is unknown. Don't forget, I told you that you use a Z test when the population variance is known. This is when we use Z test and N is greater than or equal to 30. All right? But for T test, N is less than 30 and population variance is unknown. This is the criteria for us deciding to use a T test. I have a question. I see this question. I see this sample size is less than 30. Of course, I said it with you already. That table you would see that is quite interesting to see. And I want to explain majorly the three things I want to explain in this class is number one, not really explain, but just to expose to you guys. Number one, the way to deal with degree of freedom, because when we're dealing with T testing, we use degree of freedom. So we're going to talk about that. Also, I'm going to explain to you guys how to use the table, because we're going to be having a different table entirely. All right. And also, as I've explained already, the criteria that will be needed to be fulfilled for you to decide to use a student T distribution. So we already dealt with one already. This is the criteria when your N is less than 30. So let's go on to the next one, which is degree of freedom. Now, when dealing with T test, there's something called degree of freedom, and it's nothing big. It's something everybody in this class will do easily. So degree of freedom is gotten under T test. Now, I want you guys to know one thing. You'll be dealing with degree of freedom in chi-square also, but the way to find the degree of freedom in chi-square is different from that of T test. So how do you find the degree of freedom in T test? T test degree of freedom is very simple. All you need to do is to just subtract 1 from the sample size. So your sample size, for instance, let's say it's 20. Your degree of freedom will be 19. So degree of freedom, sometimes written as V, something like, it looks like V, all right, is actually N minus 1. So this is how you find degree of freedom. Note that very much, because you would be using degree of freedom to check your value on your table, you need degree of freedom. So whatever your sample size was, go on to subtract 1 from it to get your degree of freedom. Now let's go to the third thing I said I wanted to talk about, and that's the use of the t-table. Now this part is very, very important because you really need to be, your table is like the key to solving any under t-testing. Now, let me quickly say this. The way we solved significant testing under z-test, it's just, we're going to follow the same format, just with these slight differences. When we wanted to find z-test, when we wanted to conduct a z-test, I told you guys that what you were going to do was you had your null hypothesis, you had your alternative hypothesis. I told you guys that if you had greater than, this would be a one-tailed test, a right one. If you had less than, this would be a one-tailed test, a left one. Just this alone, you will not have this in this case. But if this was not equals to, you'll be having both, which is what we call a two-tailed test. The same thing goes for the t-test, all right? Now, the same thing goes for the t-test. The next thing to do, as I told you guys there also, is to find the test statistics. I told you the test statistics is very vital. Now, I want you guys to know that the test statistics for both Z and t-test are so similar. Literally, we can almost say it's the same thing. All right, it's the same x bar minus mu naught over s over square root of n. The test statistics for the t-test, the same thing, obviously. Now, the difference will come at the point when you want to find your critical value. All right, your critical value. That means the point, don't forget what I told you critical value means. The point where you're going to decide where you're going to be rejecting and not rejecting. So let's say, for instance, your critical value was minus 2.18. Of course, you know that every value less than that will be rejected. And let's say this was 2.18, obviously. Every value greater than that will be rejected. And any value that falls between this range, that means they are not inside the rejection region, we are not going to reject. Now, this is where the difference between a z-test and a t-test will come in place, because we don't have the same table. So we're using a different table to find this our critical value. This our critical value we gotten using a t-table, not a z-table. And the way to get our t-table, our values from our t-table is different. In this case now, we're introducing what we call the degree of freedom, which I told you already is just one less than the sample size. So now, if you can, you should just try and draw up your t-table. That's like the last vital thing I want to put you guys through on, and it's actually the most important because it comes with a level of technicality I want to quickly explain. So if you open your t-table quickly, guys, you would see something. You will notice that the table I sent to you has, let me try and make this like a sample of the table. So you would see something written by the left. You would see DF written by the left. This DF stands for degree of freedom. You see DF being written there. DF, degree of freedom. Then you would see the degree of freedom ranging from 1, 2, 3, 4, and so on. It actually got to about 1,000 right there. All right. Now, this obviously is where you're going to be checking for whatever degree of freedom you got. So let's say you had a sample of let's say you had a sample of 20. Of course, if you had a sample of 20, your degree of freedom will be 19. So you go on here to find 19, whatever 19 was. All right. Is it still blur? For those of you talking about being blur, is it still blur? Is it better now? Okay. So if you had a sample size of 20, of course, your degree of freedom will be 19. So you go on to check for degree of freedom of 19. Now, this is the next most important aspect of checking the table. You would notice at the top, the table I sent to you, I did that intentionally. I sent the one that had both the one tail, you will see one tail being written here, and two tail. The reason why I sent that is because I want you guys to get familiar with both. Now, although I feel much more inclined with you focusing on using that of one tail. All right. So, but I just want to get you guys conversant with both and explain to you what's really happening around here. So when you see one tail, you would see something like on the top here, you would see something like T.50, T.75, and so on. Then you will see beneath this, you will see 0.5, you would see 1.0. So for one tail, look at it. One tail, they wrote 0.5. For two tail, they wrote 1.0. All right. For one tail, they wrote 0.25. I'm sure you guys understand the metrics. Of course, two tail will be 0.50. Then the next one we have 0.20. Then we had 0.40. This went on and on till we got to 0. The last value we had here was 0.0005 and 0.001. So what you can just see obviously is that one tail is obviously going to be the half of two tail, right? Now, so when you had two tails to be 1.0, one tail was 0.5. Of course, each of the one tail will be 0.5, 0.5. If both tails were 1.0 together, you understand that. That's quite very simple. Now, but this is what I want to now bring up because this is where it gets dicey. Let's assume you have you have a question where you had one tail. Of course, I'm going to do a quick examples. You guys, I would love you to open it and let's move together. Let's assume we're dealing with a left tail. And let's say our alpha was 0.05. So let me try and, okay, let's just try and solve some things quickly. T was 19. You see how we write it actually? Okay, let me say that quickly. The way you write it is T, degree of freedom, then your alpha value. This is the way we always write it. So when we want to check our table, we'll check for T, degree of freedom, alpha value. So here we have 19, alpha value being, let's say 0.05. That means our alpha was 5%. All right. So now let's try and check this on our table. Let's assume we are dealing with a one tail test. Now, this value, we want to check it for when we are dealing with a one tail test, and we want to check it for when we're dealing with a two tail test. And more, I want to show you how to use your table to find for both. So when we are having a one tail test, we're dealing with a one tail test now. Guys, pay attention. This is quite very, very important. Is this still blurry? Is there something? I see something talking about it being blurry. So I want to, this is the next thing I want to explain now is too vital for you to ignore, because let's say you had a one tail. I actually believe so strongly that your exam, if they are going to bring out a table, is going to be the one tail version, not the two tail version. All right. Now we have this, we have degree of freedom of 19, alpha of 0.05. If we are solving a one tail question, what are we going to be using? Of course, we go to our table. It's a one tail question. We go to our table. We go for degree of freedom of 19. Now, there are many alpha values you can see right there, but you need to be so focused on what is the tail you are dealing with. If your question is a one tail question, go under one tail now and check for what the answer will be. 0.05 under 19 should give you a value of what? 19 under 0.05 for one tail gives you a value of 1.729. 19 under 0.05. 19 under 0.05. Now, look at what's going on here. If you go and check, if you are dealing with a one tail question and you go and check this under two tail, you'll be wrong. Because using a two tail table to solve a one tail question will not work. You can't solve it that way. So you need to go and check 19 under 0.05 for your one tail table, under the one tail version of the table I sent to you. You'll see there that we have 19 under 0.05 as 1.729. So this gives me 1.729. Now, let me tell you where the issue is at. If you want to check for 0.05 under your two tail section, under two tails value will be 2.086 if you use the two tail table. That's why I'm saying it's a very critical thing to know how to use the table. So, but I want us to stick more with the one tail table. All right. Now, if you decide to solve, if you are trying to solve this for a two tail question and your alpha was 0.05, of course, you guys know that you cannot use 0 if this is alpha. If you're trying to solve for the two tail question using your two tail table, you would have to, of course, if you're using your two tail table, guys, pay attention. What I want to say, I know this part is actually a very dicey part. That's why I'm trying to break it down as much as I can. If my alpha is 0.05 and I want to use, and I'm solving a two tail question now, if I go under my two tail option on my table, I can fix in my value as 0.05 straight up. Don't forget, I'm using two tail. I'm having a two tail question. I'm using a two tail table. Of course, I don't have to break. I will just use alpha directly as this. So I will go to my two tail section. I'll go and look for 0.05. 19 under 0.05. I'm using a two tail. Don't forget, I'm trying to solve a two tail question. I'll just put in alpha as 0.05 directly. I'll be correct. But the issue now is if I'm given a one tail table, that means not a two tail table now. I'm given a one tail table, which is what you should expect. How do I find the value in that case? Of course, in that case now, since you know that alpha is 0.05, if you're having a one tail table, you would have to split that alpha into two tails. So this will be 0.05 divided by 2, 0.05 divided by 2. So now, you guys should go and check this now. Use a two tail table directly. Put the value of 0.05. Get the same answer as if you are solving for the one tail version using a one tail table. In that, not use 0.05 for a one tail table. we'll have to use 0.025. Because one tail table for a two-tail question, you would have to be considering each of the tail for not the whole of how far. So let's try and do this now. Let's look for the same degree of freedom, 19 now. If we're solving using the two-tail table, we will just go on directly to look for 19 under 0. Okay, no, let me use a different degree of freedom. Let me use T15. Let's say our n was 16. So let's find T15, 0.05. Now, let's assume we're solving a two-tail question. Let's say we had a two-tail table. A two-tail table now. Of course, I will just go on to check under my two-tail version, 15 under 0.05. 15 under 0.05, what does it give me? It gives me 2.131. So 2.131 is what I got using my two-tail table. But let's assume I don't have a two-tail table. How do I find this using a one-tail table for a two-tail question? What I need to go on to do is to divide that alpha by 2. So I'll be looking for 15 now under 0.025. 0.025, you will see it's the same value as 2.131. So this is how you solve these questions, all right? So I want to do something quickly. I want to get right into an example. So this is just what I wanted to really explain to you guys. The use of this table. Now, I intentionally sent you a table that has more of the one tail and the two tail, so that you guys can be very familiar with both. You can have both. So if they give you a two-tail table, they indicate to you that this is a two-tail table, and they want you to use it to solve a two-tail question. In that case, your alpha will just be whatever your alpha was. You don't need to be, you will be looking for, if alpha was 0.05, you will just go on to check on that 0.05, whatever your degree was. All right, directly, because a two-tail table will give you your answer for with your alpha directly. But in a case where you don't have a two-tail table, you're given a one-tail table, and you are trying to solve a two-tail question, and you are given a one-tail table for a two-tail question using the alpha under 2. That's the way you deal with these things. So let's quickly solve an example quickly. So take this question down quickly. And this is, of course, I told you already that everything around t-test is just as similar as to that of the z-test. The difference is just everything I've just explained. The use of degree of freedom and the use of a different table, and also the criteria being less than 30. All right, so the question is, the average IQ of the adult population is 100. The average IQ for a population, of course, the average IQ of the adult population is 100. A researcher believes the average IQ of adults is fewer. Don't forget, we're dealing with hypothesis testing here. So you should not forget that we are still going to be dealing with you setting hypotheses. So the average IQ of the adult population is 100. Is 100. Now, a researcher believes the average IQ of adult is fewer. Now, of course, he went on to take a random sample. A random sample of 5 adults are tested and scored. Now look at the score he gave them. He got 69, 79, 89, 99, and 109. This was the score he obtained. Now, you are lucky. In this question now, I'm not going to ask you to find the standard deviation, but I'm telling you guys that it looks like the network is not as good as it's supposed to. Can you guys hear me? Okay, are we back? Okay, so one thing you need to note here is, as I told you guys already, in questions like this, you could see questions where you are given the data point and you would be required to find the standard deviation, the mean, and every other thing you need to find. So you guys need to learn and not forget how to find standard deviations of different data points. Now, look at the question we have right here. The question then said, is there enough evidence to suggest the average IQ is lower? Don't forget, this is still hypothesis testing. We are under significant testing. So everybody adults is generally 100. All right, people had that default belief. Now, a researcher is coming up with a different premise, a different claim. He's feeling like, I don't feel the average IQ of adults should be as high as 100. I believe it's lesser than 100. So he believes that the average IQ of adults is fewer. Now, of course, I told you guys already, when you're trying to come up with a different hypothesis, you have to go on with testing samples. You can't just go on to change the default belief. You have to test. When you're done testing, if the test comes out positive that, okay, what you're saying is actually the case, then you will have to reject, you will now reject the default belief, and then obviously your belief will then be the new accepted belief. So this guy went on to take a random sample of 5 adults and tested their IQ. So the first adult obviously gave 69, second 79, third 89, fourth 99, and the fifth 109. Of course, the question is now, is there enough evidence to suggest that the average IQ is lower? That means, are we going to be able to say we should reject the null hypothesis and cling to the researcher's hypothesis? So of course, you can obviously write your null hypothesis and your research hypothesis very quickly. I believe that you guys should be able to do that without sweating. So obviously, the null hypothesis here would be that the average IQ is equals to 100, and so the average IQ is equals to 100, whereas the research is that it's less than 100. So you follow the same process that I've been telling you guys to follow, just the same way we did for the Z testing. So you want to go on now. So let me first try and find the test statistics. All right. So the test statistics, in this case now, permit me to call it T calculated. Now I called that for Z calculated. Let me call this Z T calc. These are calculated value. Because I told you it to be X bar minus mu naught, the hypothesized mean, S over square root of N. Our X bar here, you have to find that yourself. So you have to go on to find a mean for this data point. So we go on to find the mean. That, of course, you know how to find the mean there. The mean, obviously, I told you guys when you have the same intervals, the mean will be the center value in that case, if you have the same intervals on all the points. So the mean right here is 89. X bar is 89. You can go on to find that out yourself. The hypothesized mean right here is 100. Your S was given as 15.81. And your N obviously was 5. Now, guys, I forgot to say this, but why do we decide to use t-test? Can anybody write it quickly in the comment section? Why am I using a t-test in this case? What's the rationale for me to use a t-test? Why not a z-test? What's the reason why I decided to use a t-test and not a z-test? You know, you need to... Why do we use a t-test? Why is it a t-distribution? Why do we model this using a t-distribution? What's the reason why we are deciding to use a t-test here? Thank you very much. Sample size is less than 30. So our sample size here, they said a random sample of 5 adults. Our N here, 5, which is obviously less than 30. That's the reason why we're deciding to use a t-test. So if you go on to solve this test statistics, the t calculated, what did you get? Can you people punch that on a calculator quickly? Minus 1.56 is what I believe you should get. So now this is good. We have gotten our test statistics to be minus 1.56. Now the next thing to do is to go on to now try and find my critical value. All right. Now, what kind of test is this? Is this a one-tail test or a two-tail test? Of course, this is a one-tail test because you can see the alternative hypothesis has a left-hand side. This is a one-tail test and it's a left-tail test. So we're going to be having something like this. So now, the next thing to do is to find we want to find the critical value, the t-score. We want to find the critical value right here. Look at what they wrote here. They said we should take our alpha to be 0.05. Now, in this case now, guys, I need to now use this to shed some light on something. We don't deal with area and all those things. We don't say so much around that here. You know, I told you we use degree of freedom here. So for you to find your critical value, of course, when you're dealing with z-test, you will say the area here is 0.05, and you go and find the corresponding z-score that produced an area of 0.05. But in this case now, you need to go find the degree of freedom. What's the degree of freedom? That will be 5 minus 1. Right? Degree of freedom is 5 minus 1. Degree of freedom in this case is 4. All right? Degree of freedom is 4. Let that be noted. Always subtract 1 from the sample size to get the degree of freedom. Now, how do I want to find my tabulated value, the values on the table? I'll go on to find degree of freedom. What was the alpha value? 0.05. So this is what I want to go on now to find on my table. So you go on to open your table, and degree of freedom is 4. So I'll be looking for T4, 0.05. Now you'll be making use of your one-tail table. Now, what you need to find now is to go to your table, check for degree of freedom of 4, trace it under that of one tail, and look for alpha being 0.05. Can you tell me what that value would be? You trace this under. Okay, thank you very much. You got a value of 2.132. So 2.132 is the critical value. So this place right here is 2.132. Good. Now the same applies to how do you make your decision? Of course, your rejection region is anywhere from this critical value downwards. So anybody that falls within that spot will be rejected. Of course, you know this will be minus 2.132 because this is found on your on the negative side of things. I'm sure you can recognize that this will be minus 2.132. So now check your value right here, the value of your test statistics, and ask yourself, does this value fall inside the rejection region or outside the rejection region? This was your test statistics, which I told you was crucial in making your decision. This value, does it fall inside the rejection region or outside the rejection region? Obviously, you can see that minus 1.56 falls outside the rejection region because it's not within this rejection region. So obviously, your conclusion here is that we do not reject the null hypothesis. So we do not reject the null hypothesis. Our confidence level here was 95%. Of course, I told you guys already that sometimes you're giving level of significance, sometimes you're giving confidence level. In this case, now you're giving level of significance with 0.05, meaning that your confidence level was 95%. So you can conclude that with a 95% confidence or with a level of significance of 5%, we do not reject the null hypothesis, all right? And therefore, we don't have enough evidence to suggest that the average IQ is lower. So I told you already, when you are making your conclusion, tell us what confidence or level of significance you are making your decision on. Tell us what the decision is. Are you rejecting or not rejecting null hypothesis? And then also try and frame your response based on the context of the question. All right, so let's solve one more question. I just wanted to use this moment to expose you to student T distribution. All right, so you can take this question down quickly. So a company manufactures car batteries with an average lifespan of 2 or more years. With an average lifespan of 2 or more years. An engineer believes this value to be less, all right? Now, an engineer is coming up with a different hypothesis, believes this value to be less. Now, using 10 samples, he measures the average lifespan to be, to be 1.8 years with a standard deviation of 0.15. All right, so a company manufactures car batteries with an average lifespan of 2 or more years. An engineer believes this value to be less. Now, using 10 samples, it measures the average lifespan to be 1.8 years with a standard deviation of 0.15. Right? At a 99% confidence level, is there enough evidence to discard the null hypothesis? So the question now is, at a 99% confidence, do we have enough evidence to discard H naught? That's the question. At a 99% confidence, is there enough evidence to discard the null hypothesis? So can you solve this quickly and let me see what your take on this would be? So the first thing you have to do is to state your null and alternative hypothesis. From what you have here, the null hypothesis is obviously your mu being greater than or equals to 2. Because look at it, a car manufacturer, he said an average lifespan of 2. Average lifespan of 2. That means it's 2 or more, but at least it's 2. So that's the way you interpret it. It's not equals to 2 in this case because it's not saying lifespan don't mean it has to be 2 or more years. That's greater than or equals to 2. An engineer believes this value to be less. So the engineer is saying, my research hypothesis, I believe this is less than 2. So it takes a sample of 10. The average lifespan, that means X bar there was 1.8. And the standard deviation, the sample standard deviation, sorry, this was supposed to be S, not this. This was supposed to be S. It's the sample standard deviation, not the population one. So S is obviously 0.15. And then our confidence level is 99%, meaning our alpha will be 0.01. So we want to go on now to find our test statistics. Our T calculated, of course, X bar 1.8 minus mu naught 2 over S, that's 0.15 over square root of our N being 10. So if you go on to find this, you should get a value of minus 4.22. All right. Minus 4.22. So the next thing now is to go on to find the table value. You want to find the critical value now. Now, this is a left tail test. To find the critical value right here, of course, your degree of freedom here will be 10 minus 1. N minus 1 is your degree of freedom. So obviously, you are looking for T9 0.01. Because I told you, this is how you write it, T degree of freedom alpha. All right. So you go on to the table now, you find degree of freedom of 9. Using your one tail table now, go on to find whatever 9 was, degree of freedom 9 under 0.01. So I'm sure you should get a value of minus 2.82. You should get 2.82, but of course we are on the negative side of things. So that will be minus 2.82. So you ask yourself, this your test statistics, does it fall within the rejection region or outside the rejection region? Of course, minus 4.22 obviously will be inside the rejection region, somewhere around here. So in this case now, since it falls inside the rejection region, we are going to be rejecting the null hypothesis. And I told you already how to make a very good conclusion. You could say things like, with a 99% level of confidence, we cannot accept. So we can say with a 99% confidence that there is enough evidence to discard, that is, to reject the null. So that's how simple t-testing is. A brief summary of what we just did. So I told you guys already that three main things I just introduced you to. All right, everyone, take care of yourself. Bye-bye. This is where we're going to end the class. Take care of yourself. Have a good night. Bye-bye. Have a good one. The network. So this is where we end the class for tonight. I believe we are done with the teaching, so we don't have, there's nothing more to. I just wanted to summarize, and I believe you guys understand it very well. So enjoy yourself, and wish you guys all the best.